Hello. The topic for the discussion is force, friction, and mu. Like the cow says, mu. Well, this is intended to be a supplement to what we do in class, so it's not intended to replace it. So just compare your notes to what we took in class and supplement them if necessary. And if you have any questions, be sure to ask me in the morning. Okay, so let's get going. Okay, so what you see in this picture is exactly the model of what we have in class. We have here a block of wood, and I'm just going to call this block, and it has a certain weight to it. And we also have a cup over here in which we're going to place washers. This is a pulley, and it is a frictionless pulley. Now, its only job, this frictionless pulley, is to take any force, because we're going to start filling this cup full of washers and pennies and weights, and we're going to weigh it afterwards. Its only function, that pulley's only function, is to redirect the force so it looks like this. So we'll know exactly when this block starts to move because we'll weigh the pennies in here and we'll know what kind of force was pulling in this direction. Now this force has a name the way it's shown here. Okay, we have the block sitting on the table, and we have the block and the pulley, and we have the cup pulling down. Now this cup has, as we start to fill it, we'll have a force of gravity, and that's going to be equal to the mass times the gravity. Now, I'm going to show you the forces that exist right now. We're going to vary this so as we keep adding pennies, the force of gravity will start to increase. And again, eventually, this block will start to slide. Well, just so we know what other forces are also acting on this block right now, I'm going to draw them and then we'll talk more about them later. Okay, we know that right now there is a force of gravity of the block, and I'm going to call that, let's make this force, let's change this. Let's make this force gravity of the cup is equal to the mass of what will be in the cup times gravity. And we'll do that just so we don't confuse it with the mass of the block. All right? And we'll call the mass of the block, okay, and the block and the gravity, that'll be a weight of the block pulling down, and we'll call that force of gravity. Let me redo that, a different color here. Let's call that, let's try this color. We're going to call that the force of gravity of the block, and that's going to be equal to the mass of the block times gravity. So the only thing that doesn't change in these two equations is the gravity part. And let's show what the block is going to look like. Here's the block. It is going to have a force of gravity pulling downward. But since it's not moving, that implies that there is another force pulling up in the opposite direction, and there is. Call the force normal. And this one over here is the force of gravity of the block. Now, before we go on too much farther, let's recall what the force normal is. The force normal is any force perpendicular to a surface. Now, we've talked about this in class several times now. It's any force perpendicular to a surface. And the surface not shown here is like so. Okay? And the force of gravity of the block is nothing more than the mass of the block times gravity. And that's the weight of the block. And this over here is the weight of the cup. Now that we know what those are, I don't want to use them at the moment. We're going to erase this section over here because I only want to talk about the pulling forces caused by the cup. So we're going to add weights to this cup, and at some point this is going to start to move. Before we go too much farther, let me just say one other thing, that there are two forces that we should be aware of. One is the force of friction static. The S standing for static. Static meaning non-moving, staying still. Okay? And this force of friction static is what happens, is the force you have before there's actual movement. So I'm going to put over here before actual movement. This is the force holding you back before, stopping it from moving, before movement. Okay? And there is another force that is the force of friction kinetic. And like you might guess, this is the force after. This is the force of movement, the friction of movement. So the force of friction static is the one that stops it from moving, and once it's actually moving, the force of friction kinetic is what holds it back. It's still moving, but it's holding it back. So I wanted you to understand those two. And what we're going to be using is only this one over here. This is the one we care about for today, the force of friction static. What's going to cause this thing to move? And from that, we're going to develop the mu, which is the coefficient of friction. Okay, so let's go on. Let me erase this. Right this moment in time, we do not care about the weight of the block. We will, but not yet. Right now, I just want to point out a few things. Okay, right now, with no pennies in the cup, okay, here's the center of what I'm going to call my little tug of war. Don't forget, all the pulley is doing is redirecting force. Okay, and right now there's no weight, so there's no action whatsoever. There's no pulling. There's no weight in the cup, therefore there's no pulling, and everything is staying still. I am neglecting showing the force of friction normal and the force of friction of the block down. All I'm interested in is the horizontal motion right now, horizontal forces. So let's go on. Let's start to add some pennies over here. Okay, we're adding a few pennies over here. There's going to be some weight. And I'm going to show that weight like this. Okay, not too many, just a few. And that's because this is the force of gravity in the cup. And if the cup still doesn't move, it means that there must be an equal and opposite force pulling this way. We're going to call that the force of friction static. Now, it wasn't there a second ago. It occurred when the force, when we added pennies to the cup. And then this guy started to say, okay, I'm ready to pull. But the force of friction static said, not so fast, buddy. You're staying where you are, and it grew. Now, there is no acceleration, there is still no movement. Now remember what Newton said. He said that acceleration in his second law required a force for there to be an acceleration. And I'm going to make that a force net. After you subtract all the forces, if the force net is equal to 0, then there is no acceleration. And what we have here is a minus. I'm going to give this some signs here. We have a plus force and a minus force, and right now they're equal, so they are equal to 0. The sum, remember the symbol? The sum of the forces, FF force of friction static plus force of friction, a force of gravity of the cup are equal to zero. Therefore, it can't move. I can't say this enough. You must understand what this means, that if there is no net force, there is no acceleration. Okay, so let's clean this up and go back to what we were saying. Let's add a few more pennies to this, and we'll add a few more pennies by, let's see, let's change the color. We'll add a few more pennies by, let's add some pennies by adding some green here. I'm going to add some pennies, this many more pennies, okay? Okay, so now the force of gravity has gotten larger. It's bigger than it was. Can you see that? But I'm telling you, there's still no movement in the cup. So that means that the force of friction static said, listen, I see what you're trying to do, and I am going to grow till once again I am equal and opposite. Okay, so now the total of these forces looks like this again. They're both equal and opposite. So the net force is still zero, which means there still is no acceleration. Well, you know and I know this can't go on forever. Sooner or later, I'm going to add enough pennies to this so this thing is going to start to slide. So let's add a few more. Let's take this force and let's add, don't forget, here's our center over here. Let's add even more pennies. And this force over here, the force friction, says, okay, I'm going to go and, uh-oh, can't get that far. Can't get up to where we are over here. And at that point where this thing just can't quite get there, the block is going to start to slide. And it's going to start to slide because we now have a net force. The force of friction static could no longer hold on, and everything starts to move. Now, when it does, it becomes a force of friction kinetic trying to hold it from running away, from going crazy. But we're not talking about that. We're only concerned about the point, the very point where we add that last single penny where this starts to move. That's all we care about. We want to find the lowest value of a net force, okay, that causes an acceleration. Okay, so I'm going to erase this for the moment, and I want to summarize. Okay. Summarize meaning repeat everything I've said that's important so far, and see what we come up with. Don't forget, if you have any questions, write them down. What I said is simply this. I'm going to try and show it in different colors here. I said that there is basically going on a tug of war. Okay, and that tug of war occurs when I start to add pennies to this cup. Okay, I add a few pennies right here, and I end up having no longer a force of gravity of the cup that's equal to zero. It's a styrofoam cup, so I'm going to say that there was basically no weight there. And I started adding the pennies to the cup, and all the pulley does is change the direction. I could have just as easily put started pulling in this direction, but that's hard to measure. This is so much easier pulling down because then I can measure the cup and see what force there was. So the pulley changes the direction, and we start pulling in a particular direction. Okay, and I said I'm going to show this with a little tug of war. So we add some pennies, and we now have, oops, that's not what I wanted. Okay. try that again. Okay, I added some pennies and we have a little weight over here. A little force of gravity cup occurring. And we'll show that, I'll note that just by saying this is FGC, force of gravity in the cup. But as I do that, and I add those first few pennies, I notice that there's something that's going to start to grow over here, and that is a force coming out this way saying, oh, no, you're not. Okay, I'm going to stop that force by adding a little force of my own in this direction that is equal and opposite. So there's my little force going in the other direction, and I'm trying to make these just as best I can as equals. Okay, and when I say equals, it says that this force that we're going to call force of friction static in the minus direction equals the force of friction, the force of gravity in the cup, which is positive, and the net result is 0. And because it's 0, there is no acceleration. Okay, to kind of summarize, what I then said is, all right, I'll see that number you just did, and I'm going to raise this even more. I'm going to move this out to here. To make a long story short, this guy says, well, okay, if you're going to do that, I'm going to try and what I'm going to do is I'm going to change my value and go out and equal u by going out with the same, don't forget these are vectors, the same magnitude in the other direction. And again, the force is still equal to 0 when we add them both up, the minus and the negative, because they have the same magnitude. Magnitude meaning quantity. Okay, well, eventually, to make a long story short, or shorter than it would have been, I guess, if we go out and make this a little bit further, pretty soon, just a little bit sooner, a little bit bigger here, this force of friction may try, he may try and increase, but he can't. He can't go any further because he's at the limit. And the end result is this guy wins by the smallest amount. And that's what we're trying to find. The smallest amount here of added pennies that cause this thing to give way. That's where we are so far. Okay, so let us go on. I had said before that, we haven't talked about this mu yet. Okay, and I said before that we were going to be using the force normals and the force weight of the block soon, and now is the time. But first, let's talk about this mu. Mu is written kind of like a funny M like that. That's the Greek symbol for mu, okay? And it's equal to the coefficient of friction, and I'm just going to put down COEF to abbreviate it. It's the coefficient of friction. And in this case, we are talking about static friction. That's all we're going to be talking about. So I'll put an S over here so we know that we're talking static in this case. And it's also equal to a value. It's equal to the force of friction static divided by the force normal. Not net, normal. This is force normal. Okay, so now we're going to find out all about this this force normal. And notice what I've done over here. Okay, see this red line in between? The reason there is a force of friction static, by the way, is because the surface is not perfectly smooth. It's kind of gritty looking if you really magnified it. And that's what causes an opposition to the force pulling it to the right, the force of pennies in the cup. So I don't know if I mentioned that before or not. All right, getting back. The coefficient of friction, mu, is defined as the force of friction static divided by the force normal. Turns out it's always going to be less than 1. Okay? Now, at least in our case, it's going to be less than 1. Okay? Now, here's the block in question. Now is the time to consider that that force normal. But we can't do the force normal unless we know about the force weight pulling down. Okay? There is a force weight pulling down, and we're going to call that the force of gravity of the block, like we had before. Force of gravity of the block. And that's equal to the block's weight, in case we've forgotten. And we're just going to give that a value of 3 newtons. Made it up. Well, let's see. If that's the force pulling down, I don't see it falling through the table here, do you? I don't see accelerating at all. And don't forget, I'll say it again, acceleration is equal to force divided by mass. Force divided by mass. And if the force is equal to 0, there's no acceleration. And if it's not moving, it implies that there is an equal and opposite force pulling up. And here's that equal and opposite force pulling up. It's supposed to be a straight line. Okay, pulling straight up, and that is equal to a force normal. And I don't like it. Let's make it a little darker. Let's erase that and make it just a bit darker. Like I say, let's erase this and make it just a bit darker here. Okay, we want a force normal pulling up in the opposite direction. So let's do it in purple here. Equal and opposite pulling up in this direction. Okay, and in the center. In the center, that's where we're pulling from. Okay, so we know that this is the force normal. It is equal and opposite. Force normal is defined as the force perpendicular to a surface, and the surface is looking like that. And the force normal is 3 weights. Now we're also going to give this a value over here. We're going to say that the force of friction, I'm sorry, the force of friction, but the force weight inside the cup the force weight over here, remember I told you, is force weight, force gravity, and I said before we're going to do Fg, and we're going to give that a value as, let's say 2 newtons. Okay, well that means that if we plug them in over here, that our mu, the coefficient of friction, is going to be equal to the force of friction static. Now, if this is 2 newtons, okay, we're saying it took 2 newtons just for this to start sliding. Okay, and if I showed this over here, we've got 2 newtons in this direction, pulling like so. And I'm saying whatever the force of friction static was before pulling back, it was just equal, and I'm going to put this down as 2 newtons, just under 2 newtons. I'm going to put a minus, just something just under, and the thing started to move, so we know that the force of friction could not overcome the 2 newtons here. Therefore, we're going to say the force of friction static was just equal to 2 newtons, because at that point it started to slide. Everybody understand that? This is just like the example we did in class, the physical example, the model I showed you. So here's our values. We got over here our mu equal to force of friction static, which I'm saying is 2 newtons, divided by the force normal, which is equal to the force weight because it's not moving, of 3 newtons. Okay, or 0.67. 0.67 is our mu, and there are no values, no units to that. 0.67. Let me clean this up a little bit. .67 is our mu value.